Hello everyone. In this brief video, I would like to summarize one of my recent paper where I tried to revise the architecture of standard recurrent neural networks to better address speech recognition. As a result, we developed this new model called light-gated recurrent units, which normally provides better performance in many speech recognition tasks and is also more efficient from the computational point of view. Well, recurrent neural networks are actually a basic component of modern speech recognition systems. For instance, they are used a lot in the context of hybrid speech recognition, where we basically try to combine recurrent neural networks with hidden Markov models. But they are also a basic component of end-to-end systems like attention-based models or CTC-based speech recognition. Recurrent neural networks are typically based on this equation where the current state at time t not only depends on the current input but also on the previous states. Of course, our function f depends on some trainable, learnable parameters w and u, which are the recurrent weights and the feed-forward weights. Okay, to train a recurrent neural network, normally we have to unfold our recurrent architecture over all the time steps that compose our sequence, like this. Basically, at the end, you can just see the recurrent neural networks as a big computational graph where we share the parameters of our neural networks at each time step. From the output of a recurrent neural network, you can compute a cost function, and you can also compute the gradient of our cost function with respect to our trainable parameters. And you compute this gradient using the standard backpropagation algorithm that in this context is usually called backpropagation through time, because to highlight that we actually backpropagate through different time steps. So what is the problem here? One problem that arises when we backpropagate through a long chain of computation could be exploding gradient. So the gradient tends to be very, very big. This is a problem that we can easily mitigate by adding a clipping strategy to avoid the gradient to be very, very big. But the other big problem is that we may have vanishing gradients when we backpropagate our gradient through a lot of time steps. So the gradient becomes very, very, very small, and this is very bad because hinder learning long-term dependencies, which are actually very important in many applications. One way to mitigate this issue is to add in such a way some shortcuts in our recurrent architectures where the gradient can flow without suffering from vanishing problems. And one popular way to add these shortcuts is to use the so-called multiplicative gates. Well, the first model proposing to use this kind of gating mechanism is the LSTM architecture proposed several years ago, but that is still used a lot in modern machine learning systems. If you take a look into these equations, you may see three multiplicative gates called output, forget, and input gates. And their role is to manage how the information flows from the input to the output of our LSTM architecture. The most important equation of the LSTM model is this simple equation here that actually implements the shortcut idea that we have described in the slide before. Why? Because our state C can be stored and changed for an arbitrary number of time steps. In fact, if the forget gate is 1 and the input gate is 0, we can store C for an arbitrary number of time steps. And in this way, our model can potentially learn long-term dependencies. In the last year, several modifications of the standard LSTM model have been proposed. In particular, in this paper, LSTM as Search Space Odyssey, the authors have tried to do several modifications of the standard LSTM model on several different tasks, and they basically have seen that they weren't able to find a model which was clearly better than the standard LSTM model, at least for the tasks that they have tried. This confirms that LSTM is a general model that is extremely well designed, but this doesn't necessarily means that there isn't a better model than the standard LSTM model for a very specific application like speech recognition, for instance. Well, according to my speech recognition experience, an alternative that generally provides a performance similar to that of LSTM are the gated recurrent units proposed by Cho in 2014. GRU are actually a simplification of the LSTM model because we only use two multiplicator gates. The first one is the update gate, which decides how much the units update their activations. The other one is the reset gate, which decides what we can forget. And similarly to the LSTM, you can see here in the first equation that we implement the shortcuts because we can save our hidden state H for an arbitrary number of time steps depending on how the update gate is set. When I started using this GRU model in my speech recognition experiments, I asked myself, can we do something better? Can we revise the architecture of standard gated recurrent units to derive a model which is more suitable and more efficient for speech recognition? So I started studying the different components of a GRU, and after many experiments, I derived this model that I called light gated recurrent units, which is based on a simple modification, on two actually simple modifications of the standard GRU model. The first one is about removing the reset gate, and we will discuss in the next slides why this could make sense. And the other is about using ReLU activations coupled with batch normalization, and this aspect of the model is also discussed in the next slides. But first of all, why removing the reset gate? Well, if you take a look into the equations, you can see that there may be a kind of redundancy in the role played by reset and update gates. Why? For instance, if you would like to give more importance to the current input, you can both set small values of the update gate or, in a similar way, small values for the reset gate. And the same arises if you would like to give more importance to the past history. In this case, you can set very high values activations for the reset gate or very high activations of the reset gate. So there is a kind of redundancy in the role played by these gates. In fact, if we plot the average activations of update and reset gates, we can see a clear correlation between these two average activations, because update gates here follows a trend very similar to that observed for the reset gate. And this clearly confirms that the two gates are actually very redundant, and maybe we don't need both of them, we just need one. And starting from this observation, we have decided to remove the reset gate. Of course, then removing the reset gate has an impact on the computational complexity, because in this architecture we only have one multiplicative gate rather than the two which are present in the standard GRU architecture. And we have also observed, as we will see in the last part of this talk, that this does not affect at all the performance of the system. Well, the second modification is to employ ReLU activations and batch normalization. In particular, we propose to employ ReLU activation in the candidate state equation. Here, as you may remember from the previous slides, in the original model here there is an hyperbolic tangent tanh activation. In the deep learning community, usually a ReLU is preferable because it doesn't have the two saturation points that are present in the tanh or in the sigmoid activations, and it's very clear that these saturation points corresponds to very small gradients that may slow down the training of the neural network. The reason why ReLU are not so popular in recurrent neural networks is that ReLU are typically unbounded, and they may cause numerical instabilities, especially in a long chain of computations. But if we couple the model, the activation, with batch normalization, we don't observe any more such numerical instabilities, and we can effectively benefit of both ReLU and batch normalization in the same model. And of course, we can use a batch normalization in all the other part of the architecture, but this is the most important part, because we can have at the same time the benefits of the two techniques without having any numerical problem, any numerical instabilities. So these are the four equations of our model. You can see that we only have one single gate, we have ReLU activations and batch normalization. Okay, results. In this last slide, we report the performance, the phoneme error rate that we have obtained using the TWIN dataset. Of course, in the paper, we have extended these results to larger datasets like Wall Street Journal, DIRA, Chime4, TED Talks, LibreSpeech, and if you would like to take a look into the full set of results, I will strongly encourage you to read our two papers on this topic. So here you can see that the light GRU model is the best model we have seen. It is better than ReLU RNN. Here it's not really a vanilla RNN, it's a ReLU RNN where we replaced an H with ReLU activation, and we also use batch normalization. Here is standard LSTM, standard GRU. Here is the model, a model called minimal GRU, where we just remove the result gate, but we don't use ReLU and batch normalization for the candidate state equation. And the last line is our light GRU model. And you can see that there is an improvement always in our model for all the features that we have tried. And here you can see that we reach a very good performance in the teaming dataset. So this is a very interesting result because shows that this model not only simplifies the computation because it's only based on a single gate, but also improve the performance. So we are able to have a system which is at the same time more computationally efficient and also provide better performance. Just to conclude, let me say that this model is already implemented within our PyTorch Kali toolkit, and you may easily replicate the results reported in this table and in the paper. That's it. Thank you very much for your attention.